to construct a non-commutative factorial that we obtain from the unitary reducible representation of certain group. And the basic goal is to study non-commutative geometry in such a non-commutative differentiable manifold that we are still working on. So the goal of today's talk will be just to show you how to construct such a non-commutative differentiable manifold. So we haven't computed the spectral triple or Dirac operator, or we haven't studied the K-theory yet, nothing. No projective module over the non-commutative space. We have just constructed the non-commutative differentiable manifold. So I will be focusing on how to compute this non-commutative differentiable manifold from the unitary reducible representation of certain nilpotent Lie group. So that's the goal. So let me. So here is a brief outline of what I will be doing. The summary of the main results, the relevant publications. The main publication that I will refer to is still under review. And then a few words about the non-commutative quantum mechanics. Basically, because the group that I will be talking about, it can be considered as the defining group of non-commutative quantum mechanics, or if you want to call it the kinematical symmetric group of non-commutative quantum mechanics. So it's important to have a good understanding how we construct this group. And next I will show you how to compute the unitary reducible representations, I mean the unitary dual of that group using the method of orbit, and following that, and after that we will construct the non-commutative factorial from the unitary dual. So let's get back to what we want to do. Also, these are this is an article that I have submitted to arXiv very recently. It's on the plethora of representations arising in non-commutative quantum mechanics and an explicit construction of non-commutative factorial that you can find in arXiv. And based on some previous publications with myself and Professor Ali sitting in the audience, the symmetric groups of non-commutative quantum mechanics and coherent state quantization, which was published in Journal of Mathematical Physics, and the other one is a paper in Journal of Physics A titled Triply Expanded Group of Translations of R4 as Defining Group of NCQM relation to various ages. So the third paper is very important for this discussion because all the unitary reducible representations will follow from the computation from the third paper. Okay, so what is non-commutative quantum mechanics? It's abbreviated as NCQM in the next slides. It's a quantum mechanics in the non-commutative configuration space. Okay? So what we mean is that we consider a system system with 2 degrees of freedom, with 2 position coordinates and 2 momentum coordinates. So our phase space is 4-dimensional. Sorry. It's R4, even simpler, if easy. And so everybody is familiar with Weil-Heisenberg group. What happens with Weil-Heisenberg group is that you have this R4 and you centrally extend it with that phase variable theta with some appropriate group multiplication rule. If you do that, and if you compute the self-adjoint representation of the associated Lie algebra basis elements, you'll see that the commutation relations between the operators would look like this, the equation number 1, and the others are vanishing. So the only non-trivial, non-vanishing relations are these ones. Okay. So like I said, that these are the self-adjoint representations of the Lie algebra basis elements. It's important to note that the Qi corresponds to the group parameter Pi, while the capital Pi corresponds to the group parameter Qi. Okay, and the representation space is L2 of R2, and the central element here, you see that it's 5-dimensional, theta Q1, Q2, P1, and P2. The central element is a theta, which is mapped to the identity operator of on L2 of R2. Okay, so this is a very widely studied group in the literature. In contrast to this, we have another group which we studied, tried to study rather deeply, which is a 7-dimensional real Lie group with the group multiplication rule that I will show you in a minute. Besides the central parameter there, back here, theta, we will introduce 2 other central parameters here, which means that we will not just singly extend the abelian group of R4. We will triply extend it, which means that we need 2 more inequivalent local exponents. So I will tell you what it means by local exponents in a minute. Briefly recap the theory of group extension. So if we do that, then we get a 7-dimensional real Lie. And if we study the representation theory of such a real Lie group, we'll see that it's a very rich group with a lot of possibilities there, and it incorporates all the non-commutativity of various things that people study in physics. Okay, so the resulting computational relation of the 7-dimensional real Lie group that we study is the following. It's given by the equation 2. Here you see that besides the h bar thing, we have 2 other parameters coming into play. One is theta and the other one is b. Here theta is related to the space non-commutativity, and b is something related to magnetic field that we put orthogonal to the plane where the particle is constrained to move. So B is not exactly the magnetic field, it's a multiple of the magnetic field. We will find it in a moment in the sequence. Okay, so here you see that the central parameters, theta, phi, psi, they are all mapped to the identity element, identity operator on the Hilbert space, L2 of R2. Okay. So a quick recap of the group extension theory here. So if you have a connected and simple, so we keep things as simple as possible. So we take a connected and simply connected Lie group G, and the local exponents are functions here over from G cross G to the real line, obeying these relations that you see here. Okay. So if they satisfy these equalities, and so then they are called the local exponents. Okay. So there is a special type of local exponent which is called a co-boundary term if there exists a continuous function zeta from G to R such that the following holds. Okay. So then this C G prime G is a co-boundary term, and it can be expressed in terms of that continuous function zeta. Okay. So now we want to describe an equivalence relation between these 2 cocycles. Okay, and we see that the two cocycles C and C prime will be thought to be equal if they differ by a co-boundary term. Okay, so you see that C prime G is equal to C G prime G plus a co-boundary term. Okay, so then you have whole equivalence classes of these 2 cocycles. And so now the point is that it's very important. Let me go to the board.
I think that equality should be a minus sign.
Where? Yeah, in front of the co-boundary?
G prime G minus. No, I don't know what that means.
Okay, you mean the C G prime plus C?
Oh, well, you call it trivial. Okay, fine.
Okay, so this is very simple, but for completeness, I say that so we are actually interested in the projective representation of this four-dimensional abelian group. So, in other words, we are interested in the actual representation of the centrally extended group. Okay, which means that if G is a abelian group and this is the centrally extended group, okay, so we are interested in the actual representations of theta. So the group multiplication of the centrally extended group is given by the following: theta plus theta prime plus this two cocycles, okay, and GG prime. Correct. So we'll be focusing on the actual representation of this centrally extended group, which means that we are trying to find the projective representations of the abelian group. Okay. Good. Now we move on to the next slide. So here appears the three inequivalent local exponents that we need to centrally extend the abelian group of translations of R4. So these are explicit expressions of this. So in the paper that I mentioned earlier, there is a proof that these three are indeed inequivalent local exponents in the sense of Bergman. So I'm not going over the proof, but using these three inequivalent local exponents, we can construct this seven-dimensional Lie group, theta phi psi qp, and the group complementation rule is given by that equation number 3. Okay. Okay. Good. So the notations of this wage and all that is given below. All right. Okay. Now it's important to see. So if we denote the Lie algebra of the corresponding group G and C by small g and c, and the dual of that, the dual Lie algebra of that as G star of NC, then everyone knows that there is a natural action of that group on the dual of that Lie algebra, which is called the quadrant action. So here is the computation of the quadrant action of the group on the dual Lie algebra. Okay. Here is how it looks, equation number 4. Okay? So this is an important equation from which we will be able to compute all the families of the quadrant orbits, underlying quadrant orbits, everything, explicitly. So which has been done in the other paper that I mentioned in the beginning of the talk. Okay? Well, there are three polynomial invariants that you can see that are associated with the central elements, theta, phi, and psi, which are called x5, x6, and x7. Okay? And we, for simplicity, will denote by these polynomial invariants with rho, sigma, and tau, associated with the central elements. Okay, so in the sequel we will see that this triple actually determines all the quadrant orbits of the group. And this triple is actually related with the non-commutative parameter that we described with H cross B and theta. So in our approach, the deformation parameters, which are H cross B theta, appear from somehow to completely describe the quadrant orbits. Okay, these deformation parameters come from that. So here is a very quick classification of the coadjoint orbits here. Okay. So as I said that the classification of the coadjoint orbits entirely depend on these three parameters. Okay. So one class is when all three of them non-zero, and this holds. Okay, this constraint. It defines a certain two-dimensional surface in R3. I'm very poor at drawing. I won't be able to draw it here. Okay, it's like an elliptic cone-shaped surface, something like this. Okay? It's in the paper. If you are interested, you can see. Okay? So this is rho square, alpha square, gamma, beta, sigma, tau equal to 0. So which means that we are either inside or outside here, inside or outside, away from the planes. Okay. So we cannot be on the planes, on the three planes. We cannot be on this surface. And for that region, okay, for that region, if you take an R4, affine R4 space through each point, that will be our coadjoint orbit. Okay. So these are four-dimensional spaces, vector spaces. Okay. So the second one is because of this surface, the two-dimensional surface embedded in R3. So for this region, the coadjoint orbits are a bit degenerate, means that they are R2 planes here. Okay? Through this surface, you just take R4, and that inside that R4 you need two other parameters to foliate the R2 planes. This is how the two-dimensional planes are foliated inside the initial R4 space. So this is how the foliation looks here. So it's on the surface, okay? So now, you see that you are on the rho sigma plane. When you are on the rho sigma plane, means tau is 0, the coadjoint orbits are also R4 affine spaces. And when rho and tau non-zero, sigma 0, similar things happen. And when rho is 0, meaning that there is no quantum mechanical effect, we will explain it later. And just two non-commutative planes which don't talk to each other in the absence of quantum mechanical effect, the coadjoint orbits are also R4 affine spaces. Okay, now this is important. Here, just rho is non-zero. Sigma and tau both are 0. Okay, this is ordinary quantum mechanics. So, which means that in this group, the group G and C, if we compute the unitary reducible representation of G and C, we see that the representation of the ordinary Weil-Heisenberg group is sitting inside this unitary dual. So we don't have to consider the Weil-Heisenberg group separately. It's already there. Okay? Okay, so this is an important point. All right. So now just one non-commutative plane with sigma being non-zero and the other two are 0. Okay. Here the coadjoint orbits are R2 planes, and the second last is where tau is non-zero, is similar to the previous one, and the final one is through the origin. Okay. If you take the R4 plane going through the origin, then the coadjoint orbits are just zero-dimensional points there. Okay. So the underlying coadjoint orbits are zero-dimensional points there on that R4 plane. Okay, this was the classification of the coadjoint orbits. Now we try to see how we compute the unitary reducible representations of the underlying group, the group G and C, and its Lie algebra, small g and c. So it's pretty straightforward. You just apply the method of orbits. There are certain subtle things there, though when you have to choose the polarizing subalgebra and all that, you have to be a bit careful while choosing that. Other than that, it's a straightforward computation by which one can compute the unitary reducible representation associated with each quadrant orbit. They are in one-to-one correspondence by a theorem by Kirillov. So this is the sector where rho, sigma, tau, all three of them are non-zero, and they are not in that surface. Okay. So this is the most important family of representations that we will consider to construct the non-commutative photoarray. Okay? We will not consider the other ones, just these ones. Or maybe, no, sorry for that. I think we need all of them. So, but this representation corresponds to those covariant orbits, the first class of all the nine classes I told. Okay, so this is the representation of the algebra number 6. Okay, you see that self-adjoint representation of the algebra, Q1 hat, Q2 hat, P1 hat, and P2 hat. There is certain asymmetry here, as you can see. Q1 hat and Q2 hat, they are not symmetric. Okay, one is multiplication by R2, and the other one involves a differentiation and multiplication both. Okay, so I'll talk about this asymmetry in a while, where actually it means that you see that these are equivalence classes of representations. So this is one of that equivalence class. So if we take a unitarily equivalent representation in the same class, we can symmetrize it by certain gauge transformation. Okay, that I will discuss in a minute. Okay, now the important thing, what this B H cross, because there was no B and H cross in 5. Okay, B H cross and theta. So what do we mean by that? This is what it means by number 7. Okay. By number 7, so the relation between H cross theta and B with the rho, sigma, and tau is given by this number 7. Okay? And it's interesting to note that, you see that if we go back to the first slide where we had the group composition rule, you see that what do you expect alpha to of which dimension? What will be the dimension of alpha? You see that theta, phi, and psi, they are all dimensionless parameters. There is no dimension associated with them. So we expect alpha to have dimension 1 over q times p, so that the whole thing is dimensionless. And the dimension of beta we expect to be the dimension of 1 over p squared, and the dimension of gamma to be of 1 over q squared. Okay, so here we fix the dimension. So the alpha, beta, and gamma, these were required to remove these dimensional inconsistencies. Okay, this is why we introduce these dimensionful parameters. And if you look at now this expression where we connected these parameters H cross theta and B with the rho, sigma, and tau, if you plug in the appropriate dimensions here, you will see that they exactly match with the dimensions of H cross, the magnetic field, and the space-space non-commutativity. So in other words, we just didn't try to compute obtain the mathematical results. We also tried to keep it in agreement with the physical results also. Okay, so here you see that that this B is the magnetic field. The curly B over H cross is the magnetic field. Okay? And it is applied normal to the Q1 hat, Q2 hat plane. Okay, so now the second class being all three of them non-zero and they are on the surface. Okay. So here the unitary reducible representation is defined like this, equation number 8, and the representation space is no longer L2 of R2, it's L2 of R. Okay? So So in order to compute this unitary irreducible representation, we had to choose a different polarizing subalgebra, so which was not very easy to find. Okay, so the associated representation of the universal enveloping algebra looks like equation number 9. Okay. But I must say that, so in the literature, one finds that when h cross square minus b theta is 0, it's a degenerate situation and no irreducible representation can be found. But indeed, there is a representation here, actually. There is a representation here, which is not on L2 of R2, but on L2 of R. Okay? Okay. Now I will I will say a few words about the gauges involved here, because like I told you before in equation number 6, that there is a certain asymmetry appearing here between Q1 hat and Q2 hat. We can remove this asymmetry by introducing some gauge, like I promised before. So here is a discussion on that, gauges of non-commutative quantum mechanics. Okay. So everyone doing physics is familiar with this B being, the magnetic field being equal to this curl of the vector potential, right? Which in other words, for the two-dimensional case, it reduces to del 1 of A2 minus del 2 of A1. Okay, so now this vector potential A, how many choices are there for A which will satisfy this equation? Many choices. So one of them is what? B x2 0 minus I don't know. Okay. So you can check it. Okay. So if you del 1 A2, let me write it. Equal to del 1 A2 minus del 2 A1. Okay. So if we take A2 to be A1 0. If we take A2 to be B X, okay, then it satisfies. So also you can try this B over 2 Y minus B over 2 X, something like this, okay? You can check it, okay? So this symmetrized situation corresponds to the symmetric gauge, and this one is called the Landau gauge in the literature. So, okay. So here you see that in our approach, this is for the commutative case, and in our approach, this is non-commutative quantum mechanics. So we have to refer back to the non-commutative position operator, okay? Q2 hat. So Q2 hat can be obtained from here, from equation 6. You see, this is R2. So if you plug it in there, here, you will get B on both sides of equation 10. All right? So this is the Landau gauge, the famous Landau gauge introduced in non-commutative quantum mechanics. It appears in many literatures, okay, which have been written in the last decade. So the natural question, sorry for the two questions. So the natural question to follow immediately, if there is any other choice of gauges associated, okay? So in order to understand these gauges, we need a theorem, okay? So the theorem is the following. So a continuous family of unitarily equivalent. Now we are no longer unitarily inequivalent representation that we computed all by using method of orbits. Now we restrict ourselves to a certain quadrant orbits associated with rows equal to sigma equal to tau equal to 1, okay? Which means we are in one quadrant orbit. So there is an equivalence classes of unitary irreducible representations there, okay? So I refer to that equivalence class of unitarily equivalent representation. So I'm sorry for that. So they are all unitarily equivalent, right? That's the equivalence class we are discussing about now. So these class of unitarily equivalent representations is given by this expression. Okay, and you see that this is a two-parameter family of representations, L and M. They can take any value from the real line. Okay, and F is in this Hilbert space, L2 of R2. Right? Okay, so the proof is rather simple, but maybe a little lengthy computation you have to do to check that it holds. Okay? So now this is the corresponding representation of the universal enveloping algebra. You see that both the parameters appear here, L and M, of the family of unitarily equivalent representations. So you can check that if you plug in M to be 0, you will get the Landau gauge representation. So you can plug in any M to C, any M or L to C if they are actually the representations of the underlying group. Okay, so this is the commutation relations of the self-adjoint realizations of the Lie algebra basis elements. Okay, as you can see that L and M does not appear here, which means that they were indeed representing the gauges of the non-commutative quantum mechanics. Okay, they don't make their appearances here. Okay, so now we give a short lemma where we say that the one parameter family of vector potentials AM given by equation number 14 satisfied equation number 10, this one, B equal to del 1 A2 minus del 2 A1, and hence AM can be rightfully called the one parameter family of NCQM gauges. Okay? So these are the NCQM gauges that we wanted to find. Okay? So you can plug in any M here and see what that vector potential, the corresponding vector potential is. So I think there is a remark here.
Excuse me.
Yeah.
Guarantees that these are the only possible choices of gauges which give you equivalent representations. I admit that this choice of gauges give you unitarily equivalent representations. But are you sure that this is the only possible way to get unitarily equivalent representations by changing the gauge?
But if we restrict ourselves to this quadrant orbit, the four-dimensional quadrant orbits, this is the only way we can get all possible gauges.
What makes?
Okay.
Why should the M and N be integers?
No, they don't need to be integers.
Oh, okay.
They can be anything.
Okay.
They don't need to be. So it's a continuous family of gauges. Okay? But in literature, we find only the Landau and the symmetric gauge. But we find here that there is a continuous family of NCQM gauges, not only just two. Okay? It's even, much more than that. Okay, so here is a remark. You see that when L and M are both 1, then we get the Landau gauge. And when M is 1/2 and L is this number, we get the symmetric gauge. But you can check that the alpha times alpha minus square root of alpha square minus gamma beta over gamma beta is dimensionless by computing the dimensions like I said before, okay? So which is in agreement with the dimensions of these parameters, okay? Of this constant, dimensional constants, gamma, beta, and alpha. Okay, so it is important to note that gamma, beta, and alpha, they are not changing. The only changing parameters from one quadrant to the other quadrant orbit are rho, sigma, and tau. We are keeping these alpha, beta, and gamma constant just to match the dimensions, okay? They were kept into they were brought into the picture just to for dimensional consistency, nothing more than that, to make it more physical. Okay, so we are in the last segment of the talk where we discuss how to construct a non-commutative 4 tori out of this the unitary dual that we discussed in the previous slides. Okay. All right. So first of all, by the way, how much time am I left with? Okay. Okay. So here is the general definition of non-commutative 4 tori. A non-commutative n tori, okay, or the algebra of smooth functions on the non-commutative n tori. Okay. So here I have to say a few words about the non-commutative n tori. So it's hard to sometimes, you see, even for the quantum group, it's hard to understand the structure of quantum groups. So what one study is the smooth functions on the quantum group, and try to understand the structure of the quantum group by studying this algebra of functions on the quantum group. Because nobody really understands how quantum groups look like, so it's better to understand the functions. So we will be dealing with the functions over the non-commutative 4 tori instead of the non-commutative 4 tori itself. Okay? And see if under the classical limits it goes back to the commutative C-star algebra of the smooth functions on the ordinary 4 tori. Okay? So this is the goal. So here we will denote by A theta this algebra, the non-commutative C-star algebra of smooth functions over the non-commutative 4 tori. Oh, this is the definition of n tori. I'm sorry. So so here is the definition. So it's these algebra, this non-commutative C-star algebra is a family of non-commutative C-star algebras, because if you make theta, if you fix the theta, you will get one non-commutative C-star algebra. But if you vary theta, you will get a family of non-commutative C-star algebra. So all these, comprise the non-commutative n tori. Okay. So these algebras are generated by n unitaries which satisfy these relations. Very simple. You have n unitaries and they satisfy this relation, and you take the enveloping C-star algebra generated by these unitaries. That's your non-commutative n tori.
Sorry, why do you write it as C infinity of something? I mean, it's not, it's not functions on anything. It's just an algebra generated by these unitaries.
I'm sorry.
Because if it were a function, algebra of functions, that would be commutative.
No. Okay. So this is the definition of the non-commutative n tori.
Okay, fine,
but not. Okay. So but A theta is the. Okay. So here you see that I understand your question. So it's clear that it's infinite dimensional. Okay. And it will be, so you take the PPW basis, all the monomials, they will form a vector space. This is that vector space.
Which monomials?
The monomials in these U's.
Okay.
And then you form a vector space. That's an infinite dimensional vector space.
Yes.
That's what I call, that's the C infinity of T and theta.
It's not okay, it's a vector space, it's not some class of function.
So this is how it's defined, okay? So when you have these all commuting with each other, the U's, then it approaches the commutative C-star algebra.
Okay, but I just find that notation confusing because it looks like some functions and some space, and it is not.
Okay. All right. So theta is this Q symmetric n by n matrix, and theta jk are entries of that matrix. And when theta is the zero matrix, as I said, that it is just the C-star algebra generated by UJs, which is commutative, and can be identified with the continuous functions on the n torus, okay, in the classical limit. Okay, so we are particularly interested in the case when n is 4. Okay, so the 4 torus. So in our case, we have 4 generators: U1, U2, U3, and U4, and there is a certain matrix, 4 by 4 matrix, which is a skew symmetric matrix, and we will be able to compute these generating relations of equation number 15 using using the unitary dual which we computed here. Okay. Here, okay. These unitary operators, number 5. So I didn't mention the other families of unitary operators here though. Okay, so let's see how it looks like. So, so these are one parameter groups of unitary operators that you obtain from the unitary irreducible representation of the group GNC. Okay, so this is how UQ1 acts. So equation number 16 tells you how UQ1, UQ2, UP1, and UP2 acts on function from L2 of R2. Okay, this is how it acts. So now it's very exercise to see that number 17 holds. All right. So now, so far we have been dealing with unitary irreducible representation of some group. Okay. Now we need just 4 operators. Not even operators. We just need 4 unitaries by which we can generate a non-commutative C-star algebra. That's it. We don't look at. I think this is the question you asked me, Prof. Ali. So we don't consider. We are no longer with the group representation here. From this set of relations, 17, we want to form 4 unitaries that will generate a twisted group C-star algebra. Okay? Okay, so now by easy substitutions, we form equation number 19, where you see that U1, U2, U3, and U4 obey these defining relations. Okay, as you can see. So from which, yeah.
Those P1, P2, etc. uniquely fixed. Oh, you have 4 equations there.
Yeah. Okay. So now, following equation 19, you can find this matrix, skew symmetric matrix that I started with, that I gave in the definition, okay, of non-commutative tori here. So this theta, okay, this theta, this theta. So we have an explicit expression of this theta here, correct? Okay. So using the other representations, the unitary irreducible representations of G and C, one can compute the other expressions of this skew symmetric n by 4 by 4 matrix. Okay, so I haven't written it here, but we denote the family of C-star algebras generated by these unitaries obeying the relations 19. Okay, this 19 by a sub theta rho sigma tau, which means that as you go from this, in this R3 space, as you go from one point to another point, you get different C-star algebras. Okay, each of them is infinite dimensional, and together they give the non-commutative photon. All right. This is hard to look at, but this is how you get the whole family of non-commutative C-star algebras. And under classical limit, these all approaches to one commutative C-star algebra where everything is 0. Okay, that is also infinite dimensional. So here I write how we can find the using similar technique we can find the other relations. Okay, so here is a theorem defining, stating how we find the non-commutative fortiori, okay, using the unitary rule of G and C. Okay, so everything follows from these two skew-symmetric matrices. Okay, when rho, tau, sigma they are 0, they follow from the first one. So the only non-trivial situation is the second matrix, where we are on this surface. Okay, so that's why I just separated the statement into two skew-symmetric matrices, because the second one cannot follow from the first one. Okay, so it means that when you see that here, so this applies. This will be the 4x4 skew-symmetric matrix when the rho sigma tau is not on the surface. The surface is parameterized by rho and zeta. Zeta is another parameter. Okay, that you can understand from here. And when it's on the surface, then theta is given by this to generate the C-star algebra, the infinite-dimensional non-commutative C-star algebra. Okay. All right, so this is the last part. So we are almost finishing. Now that we have the non-commutative, so we have the non-commutative. We have the non-commutative differentiable manifolds, which we denote by t theta 4. Okay, so if we take two functions on the non-commutative fortiori, we denote them by f and g. The star product between them is given by this expression. Okay, where so you see that here I have introduced a twist here by this sigma. This sigma actually is given by, okay, this exponent, which is the 2 cocycle on this abelian group of Z4. So it's a map from Z4 cross Z4 to T, the unit circle. Okay, it's an easy exercise to check that it's a 2 cocycle. All right. And that theta RS is given by this. And this small theta, this small theta is the 4x4 skew-symmetric matrix that was given by that theorem, the earlier theorem. So this is how you get a non-commutative star product between functions on the non-commutative fortiori. And you see that it's interesting to see, which I think I have. Okay, so so one can immediately see that this non-commutative C-star algebra is nothing but the twisted group C-star algebra. Okay, Z4 sigma. You twist it by this one, sigma. Okay. So in general we have an integral here, integration here, but it's an abelian group, so we have a sum here. And without this sigma, it's just ordinary convolution. Ordinary convolution gives you a commutative C-star algebra. So when your theta goes to 0, you get a commutative C-star algebra of convolution, which is the group C-star algebra, which is of course commutative. Okay. So in the classical limit, when all 3 goes to 0, the skew-symmetric matrix theta approaches the 0 matrix, making the non-commutative twisted group C-star algebra approach the ordinary commutative group C-star algebra, C-star Z. Okay. This is what we wanted actually. Okay, so what we want to do next. So these are very, very vague things. Okay, yeah, I haven't looked into these things yet. So if you ask deep questions to me, I will not be able to answer. So I'm still in the process of studying these things. Not all such algebras for different skew-symmetric 4x. So I have computed, I have shown you how to compute these 4x4 skew-symmetric matrices from the unitary illustrative representations of G and C. So now the question is, there is a notion of Morita equivalence from the Japanese mathematician Morita's theory, which is slightly weaker than the ordinary isomorphism of categories. So which means that you study the equivalence of these C-star algebras by means of the equivalence of the modules, okay? The category of modules. Okay? If you have two sister algebra, if you have the category of left, say left modules, if you take a category of left module of A is equivalent to the category of left module over B, then you say that they are Morita equivalent. So it's actually important to compute it because physically inequivalent spaces are Morita inequivalent. Okay, so it's important to know which are Morita inequivalent. It's explicitly computed for can be computed for the two torus case, where one can see that when theta is irrational, okay, they are Morita inequivalent. So in this case, instead of a number, we have a 4x4 matrix. So we have to define appropriately what it means by rationality and irrationality. All that, okay? So these works are still in progress. Okay. Also, so there is a notion of point irrationality, which means that at least one of the entry of the skew-symmetric matrix is irrational. Then you call the matrix to be quite irrational or something like that. So we are in the process of studying it. Okay, so like I told you before, that it's very vague and it doesn't probably make sense to some of you. So next, we like to study the spin geometries on T4 theta. Okay, so Professor English talked about the spectral triple and the spinor bundle and all these things. Okay, so we want to study these things and compute the Dirac operator explicitly in this situation. Okay, so like I said, so it's also it would be also interesting to see what the cyclic homology turns out to be in this place explicitly, and also we want to compute the theta function here, which I discussed with Professor Shishanmir a few days ago. Okay, so see, here is a list of some useful readings. Okay, so the book that I like the most is The Elements of Noncommutative Geometry by Jose M. Garcia Bondia et al. So you can have it. It's a very nice book to read, a very thick book, 794 pages. And I'm sorry that I did not add the references here. There is a paper, I don't know where it appeared, I have to check it. Morita Equivalence of Multidimensional Noncommutative Theory by Mark Riefel and Albert Schwarz. Okay. This is of also some importance if one wants to study the Morita equivalence of sister algebras. And Noncommutative Geometry and Quantization by Joseph Varilli. Okay, one can also look into that. It's a nice manuscript. And Theta Functions and Non-Commutative Theory by Albert Schwarz. It's also a very nice article. And Classical Theta Functions and Non-Commutative Theory by Alan Weinstein. And finally, the classic one, Projective Modules of a Higher Dimensional Non-Commutative Theory by Mark Riefel. Okay? Thank you for your patience.
So is there any questions? We have another 8 minutes. Okay, I think if there are any questions, then we thank the patient for it. Before we finish our session today, I would like to invite the Janka team to give a token of appreciation